Welcome back to Bio 6612. In today's lecture, we're going to talk about an introduction to generalized linear mixed models. There are a couple optional readings here that can help give some more background on the topic. So far, there are a couple of models that we've talked about for longitudinal data analysis, including GEEs, LMMs, and GLMMs, which is what we're going to talk about today. So with GEE models, you have a population level interpretation that's analogous to cross-sectional models, but no subject-specific interpretations. There are robust standard errors, meaning that inference can be good even if you don't have a good don't know your working correlation structure, at least under the right conditions that satisfy the sandwich estimator. And you can use different exponential family outcomes. It doesn't just have to be for continuous data. Linear mixed models, on the other hand, give both a subject-specific and a population-level interpretation, and they can flexibly handle imbalanced data more so than GEs, but they're for continuous outcomes only. So generalized linear mixed models then, or GLMMs, are the extension of LMMs to exponential family outcomes. That should be an LMM there, not GLMM. And they still have both subject-specific and population-level effects like an LMM does. Though the population-level interpretations can get complicated when you have a non-normal outcome. And they have the benefit over GEs that they can be better for missing and irregular data. So just a refresher on the structure of the linear mixed model. The model structure is given here where you have some outcome yi, which since it's longitudinal data, that is a vector of responses for the ith subject, where you'll have ni different numbers of responses for each subject. Xi is a design matrix for the fixed population level effects. Beta is a vector of regression coefficients for the fixed effects. Zi is the design matrix for subject-specific / random effects. Little b sub I is the vector of random effects. And then you also have a measurement error, or a vector of errors for this model. And the assumptions that go along with the linear mixed model are that all of the random effects are independent of the errors, the epsilon terms. We also assume that the random effects follow a normal distribution with mean 0 and G, which is a covariance matrix, giving the variance of each of the random effects and the covariance between those effects. And the epsilons also follow a normal distribution with mean 0 and some variance, sigma squared, and they're independent of each other, the epsilon terms. So generalized linear mixed models extends the conceptual approach of linear mixed effect models to other outcomes other than just continuous data, just like GLMs extend the linear model framework to other outcomes. And they're the same in the sense that we still assume both fixed and random effects in our model. And conditional on the random effects, we assume the responses for a single subject are independent and follow a distribution in the exponential family. The model assumptions are written down here. Given the subject-specific effects, bold BI, those are your random intercept and random slope terms. We assume the outcome Yij is independent and follow an exponential family distribution, and that is actually written out here. So conditional on the random effects, the outcome has an exponential family distribution with some set of parameters, theta. And the within subject correlations that are induced by measuring the outcome multiple times within a given subject are captured by the random effects. And these also follow a distribution, which is, they assumed to be normally distributed with mean 0 and the variance covariance matrix G. And this is the same normal distribution assumption that we place in linear mixed effect models. So the model itself takes the form that's given here, where on the right-hand side you see similar terms to what we saw in the regular linear mixed effects model, where you have a design matrix X for the fixed population level effects, a vector of regression coefficients beta for the fixed effects, and the design matrix for the subject-specific or random effects Zij, as well as a vector of random effects. What's different about this model is now we have a link function G, which is the function that links the response to the linear predictor in the same way it did for GLMs with cross-sectional data. The simplest example is a continuous response. The LMM model is a subset of the GLMM model. And so when we assume that the outcome given the random effects follows a univariate Gaussian distribution, the GLMM model reduces to that linear mixed effects model, where in this case G is the identity link, and we have the additional assumptions given below. The most common example for a non-identity link is the logistic model, and this is an example of a GLMM for binary data. This, in particular, what I've written out here is a logistic model with random intercept terms, where on the right-hand side you have, and one covariate xi. We have one covariate and a population level of beta 1, which is the slope for that covariate. We have a population intercept here, and we have a subject-specific random intercept here as well, which is that BI term. And on the left-hand side, this looks a lot like what we saw when we were talking about logistic regression, where you have a logit link for wrapping into the expectation of your data. Where in this case, for binary data, the expectation of Yij given Bi is the probability that Yij equals 1 given the random intercepts Bi. And the variance for this model comes from the Bernoulli or binomial distribution and is given by what we've seen before. This was sort of pi times 1 minus pi. That's the expectation of Yij times 1 minus the expectation of Yij. And we still assume that our random intercepts here are normally distributed. Another common example of a GLMM is a Poisson model, which is a GLMM for count data. In this case, I'm giving a Poisson regression model with a random slope and a random intercept, and where there's only one covariate in this model, and the covariate of interest is time, denoted Tij. And like the model in the previous slide, on the right-hand side, you have your linear predictor, which looks similar to how it looked in the linear mixed effects model. In this case, we have Tij, the covariate of interest, a population slope beta 1 on that. We also have a subject-specific random slope on that covariate as well. We have our population intercept, beta 0, and we have our subject-specific random intercept, B0i. And on the left-hand side, since we're assuming a Poisson distribution, our G, link function G, is a log link. And you could also include offset terms in this model the same way that we did when we included offsets in regular Poisson regression. But in this case, and the way I have it written here, I haven't specified an offset for this model. Then the variance for this comes from the Poisson distribution and is often given by the variance is equal to the expectation, because that's the variance for the Poisson distribution, though the default in many packages for estimating GLMMs is actually to estimate an over-dispersion parameter as well, which would be phi times the expectation. And we have the same assumption of our random effects being normally distributed here. So I won't go into detail with how the GLMM parameters are actually estimated because it can get quite complicated. But like in LMMs, for GLMMs, we need to estimate both the fixed and random effects using the distributional assumptions that we put on the model. A couple ways for estimating GLMMs are first to take the conditional likelihood. That's your Yij given Bi has an exponential family likelihood. That's the conditional likelihood. Then use Bayes equations to estimate the full likelihood based on the conditional likelihood, and use Bayesian inference via Bayesian hierarchical models to estimate the parameters from the full likelihood. Another approach is to use the EM algorithm to estimate the parameters from the full likelihood. But in general, these computations are quite difficult and require numerical or Monte Carlo integration techniques, which we won't go into for this course. So finally, some notes about GLMMs for this portion of the lecture. In the next lecture, we'll get into the actual implementation and interpretation of these models. That in general, GLMMs are most useful when scientific objective is to make inferences about individuals rather than population averages. And this is because for link functions other than the identity link, the population average interpretation can get sort of complicated with GLMM models. So unless you're looking for the individual interpretation specifically, it can be better to use a GEE model when you have a non-identity link and you want to do a longitudinal data analysis.